Okay, in this screen recording we're going to look at the effects of resistor tolerances inside the differential amplifier and looking at common mode rejection ratio. So we'll start off with some definitions. V out is equal to A V1 plus B V2. We defined that before, quite straightforward at the very beginning. We then worked out what the differential gains A and B would be in respect of common mode rejection ratio. And finally we've worked out what the differential amplifier does in terms of all the resistors. So now if we put all of those together, we can actually effectively calculate what's going to happen inside our design. So we want to know A, okay, first off. So if we look at this term here, this gain factor here, all of these, they're effectively going to be our A term. And effectively we've got a -1 here, that's going to be our B term. So if we write those out, A is equal to R4, R1 plus R2, all divided by R2, R3 plus R4. That's our A term, and our B term picks up -1, okay? -1 because we've got the negative sign there. Now if we put those two factors, those two A's and B's, into the second equation, we can now calculate common mode rejection ratio. So the common mode rejection ratio is 1/2 into A. So we need to put A down. A is this term. R4, R1 plus R2, all divided by R2, R3 plus R4. Okay, and we have -B, and B is -1, so we have +1, all divided by, and now we put our A term again, R4, R1 plus R2, all divided by R2, R3 plus R4. Okay, let's just expand that term, and now we've got +B, and B is -1, so -1 goes down here. So there's our new expression for common mode rejection ratio. If we now multiply in the numerator term here, if we multiply by R2, R3, R4, this bracket here, it'll go over to this side, and if we multiply in the denominator by this one, it'll go over here. We can then do some expansion later. So common mode rejection ratio equals 1/2 into R4, R1 plus R2 plus R2, R3 plus R4, all divided by R4, R1 plus R2 minus R2, R3 plus R4. Okay, so now we can see what's happening on the numerator, what's happening on the denominator. If we expand out all those terms and cancel, we're going to end up with common mode rejection ratio is equal to 1/2 into, so here we've got R1, R4, R2, R4, R2, R3, R2, R4. Okay, so we can add, we've got two R2, R4s, we've got one R2, R3 and one R1, R4. So what have we got here? R1, R4 plus R2, R3 plus 2 R2, R4, and that's all divided by, well, what does this denominator expand to be? R4, R1, R4, R2, R2, R3, R2, R4. R2 and 4 will cancel because of the minus sign this time, so we've got less terms on the bottom. We've got R1, R4 minus R2, R3. Okay, so we've gone from the very beginning here, and we've got this expression down the bottom. What we're going to need to do now is we're going to need to actually work out what we're going to do with some of those resistors. Well, as we've already said before, we often put them in sets and pairs. I'm going to make the grand assumption that R1, R2, R3, R4 all R plus or minus delta R. So they're all set to the same value. They've all got a resistance plus a tolerance band. Okay? And we can define that delta R over R multiplied by 100 would equal the tolerance of the components. Okay? So we're going to use that in the next expression. And we're going to take this equation here and substitute for R1, R4, R2, R3, R2, R4, so common mode rejection ratio is a half into, well, where we had on the numerator before, we've now got 4 delta R squared, all divided by, on the bottom we've got R plus delta R, R plus delta R, minus R minus delta R, R minus delta R. Expand that a little bit. If we now just expand those denominators, we end up with a half into sorry, this numerator is not delta R, it's 4R squared, okay? 4R squared, all divided by, we have an R squared plus 2 delta R times R. Delta R, remember, being the variation, plus delta R squared minus R squared plus 2 delta R times R minus delta R squared. Okay. If we now look, we've got delta R squared and delta R squared, they cancel. We have R squared and minus R squared, they cancel. We have 2 delta R times R and 2 delta R times R, so this whole thing simplifies to 4R squared, all divided by 4 delta R times R. Okay. If we cancel those terms, if we cancel the R squared with the R squared with the R, we cancel the 4 with the 4, we are now left with a fundamental value of common mode rejection ratio is equal to a half into R, the resistance value, over delta R, the actual value. So the perfect value over the actual value. If we now go back and substitute back in what we saw before about tolerances, we now end up with the fundamental equation 50 over tolerance. Okay, as a percentage. Okay, so whatever the percentage is, 50 divided by that percentage gives you that value. So this part here now is the fundamental equation that you need to remember. You need to be able to get to here, because this basically tells you what's happening in your circuit. For a differential amplifier, where you use 1% resistors, you've got 50 over 1, so you've got a common mode rejection ratio of 50. You may put that into dBs, you may leave that as a ratio, but again, that's what's causing you your problems in your design. If you have a 0.01% resistor, then you have a common mode rejection ratio of 50 over 0.01, 500. So again, it becomes a lot better. I've got a graph that I put in the lectures as well, which shows you exactly how that progresses. But you can see from the numbers here exactly how that fits. So that's what happens in your design with resistor tolerances.